Well, this is week 3, the first lecture, and today what I would like to do is discuss several items. Let me go ahead and talk about A and B first, and then we come back and later on, after I'm done with A and B, I'll come back and talk about the item C. So for the last 2 weeks, every problem that we had done dealt with the static analysis. So today we're going to start a very simple problem, which is the dynamic analysis or a natural frequency calculation, actually. And it's pertaining to the chapter 22 of the finite element book, in case you're referring to it. The only thing is that in chapter 22, I am using I'm using something called smooth VP, and this VP does not stand for vice president. It's virtual part, smooth virtual part. It is unnecessary to introduce that at this point. So what I'm going to do, I'm going to completely ignore the way smooth virtual part is used, whatever it is used to solve this problem. Okay, and let's move on. The problem that you want to do is a beam-like object with which is 10 inches long and 1 by 1 cross section. And what I like to do, and it's simply supported as you see at the top, what I like to do is to solve this thing and find the natural frequencies of vibration of it. There is an analytical solution for this problem. The first bending natural frequency can be found from this expression that generally you cannot find that in introductory courses. You get an intermediate course in vibration or a intermediate course in stress analysis. You may see these things there. But these are only bending vibration, in other words, up and down vibration, not axially, not torsional. And I'm going to solve this thing with both beam and solid elements. In this expression, notice that the density of the material comes in, the cross-sectional area comes in, E, Young's modulus, and I, the cross-sectional moment of inertia will show up. Now, as I said, I'm going to solve this thing in both with solid and beam elements. So let me start with solid elements first. This is made out of, at least the one that I want to try, made out of steel right there. So we go there, we start with the part fire. Okay. And then immediately I save this thing, file, or is that file, save management, save as, desktop, a new folder. And I'll call this thing beam frequency solid. Okay. Very good. Let's say okay. So on a convenient plane, on that vertical plane, I will sketch a square which is 1 inch by 1 inch. So let me dimension this. Okay, exit, and then pad it by 10 inches. There. I will talk about the issue of symmetry in a few minutes, okay, after I'm done with this, because I'm saying, notice that he's saying suppression of vibration modes, maybe because of the symmetry consideration. You should be careful about it. Okay, good. So we're going to apply material to it. Let's make it out of steel. So steel is here. We apply material on it, and we are pretty much done. Now, exit. What I meant is that switch workbenches, analysis and simulation, generative structural analysis. Now notice that we are not doing static analysis. We are doing a frequency analysis, okay? Let's not worry about the third option, free frequency analysis. Let's not worry about it. Frequency analysis, we say okay. And notice that because of the size of this piece, certain default element size was selected. It may be, you may have to, there may be a need for you to change it right now. Let's make it linear. Okay, let's make it linear. And then we come back and do it with parabolic, because I want you to show how the results may differ. Let me change the rendering here to the third one, which is just the part. Good. Now, being simply supported, what I'm going to do is I'm going to pin this edge. Okay, pin this edge. So what do I mean by that? Essentially pinning that edge is almost the same as clamping that edge. Okay. Although you have to realize that if there's a true pin here, this can actually shrink in the depth direction, in this direction. In the direction X, it may shrink, but this will not let it shrink at the bottom of that. But for the present problem, it really doesn't matter. It doesn't matter that much. Okay. And then this edge is allowed to move horizontally. Horizontally means in direction Y because it's on a roller. Okay. So you click on that, select that edge, but say you cannot move in the direction Z or X, but you're free to move in the direction Y because it's essentially a roller. Let me save my analysis file. So file, say management, analysis, save as. It's the right folder, beam frequency solid. Very good. It's going to go in there. Let me say OK. Now notice that loads are dim because when you do natural frequency calculation, essentially we talk about free vibration. There's no load on it. That's why there's no load. Whether you want it or not, when a frequency analysis has been created, loads are not going to be part of the game. All right, let's go run it and see what happens. So what happens by default, it calculates 10 frequencies, the first 10 frequencies, okay? Some of these may be useless to us because they may be axial, they may be torsional. We are interested only in the bending frequencies. So let me click on this deformation right there. And if I double click on this deformed shape or on the screen, double click here, it says under occurrences, it gives you the first 10 frequencies. And if you want more, you have to ask for more. Now, this is the first bending frequency. And it's 10,000 or 1,098 hertz. Okay. This one is out of plane bending. Out of plane bending. Look, this goes out of plane. This one is second bending frequency in the YZ plane. This is out of plane. This is again third. This is let's see now. This one is also in the plane that you're looking at. This is torsional. You can see that. For example, if you look at this and animate it, you can see that the torsional effect. Now we don't want this. So anyway, my point is that you get 10 frequencies. The only one that you're interested in, the first natural frequency, right there. And if you want, you can actually animate it. It's going to be like that, isn't it? Very good. Now, what about displacement? This is the deformation. What about displacements? Well, you're going to get like that. And if you say, show me the average ISO, this is the first bending frequency that we're interested in. And the displacement is, let me change the rendering here for you. Material shading. Right. Look, 48 inches. The whole thing was 10 inches. This is 48 inches. And that tells you something. If you have any experience with vibration, it tells you that the displacements are totally nonsense. And so are the stresses, because these are stresses which are based on 48-inch displacement. The shape is okay, and the actual frequency is okay in hertz or in radians per second, whatever you ask for, but these numbers are totally useless. Okay? So let's go back actually to that first frequency here. Let me undo this. First plot, that's what I meant, not first frequency. Double click on the deformation. So this is the first one, 1098 hertz. Let's keep it here. And let's go back to our theoretical derivation here from these advanced or intermediate book. You plug in the information that you have for steel, and you're going to get 900 hertz. Here, we got 1098 hertz. Here, and an analysis based on the formula that you saw, which is also involving approximation, is 900. It's too bad, about 10%. Now, let's go ahead here and change change the type from linear to parabolic and run it again and see what effect it has on the frequency. Let's see. Okay. And activate this. Double click on it. 860. You see? 860, almost 861 versus 900, analytically based on essentially beam bending theory. Let's do one more thing. Let me go and take a smaller size element, parabolic. So maybe I make it 0.3. Say okay. Run it. In the class, I talked about why is it that you may be interested in these frequencies. The first one that comes to mind is you want to avoid resonance. If you know these frequencies, you can try to avoid resonance or improve your design. Okay, double click on it. It was 860, now it's 856. So it doesn't affect the size, does not affect it that much. But anyway, so that's the first problem, using solid elements. All right, so let me save this and get out of it, because I want to repeat the same problem with beam elements. I'm going to close this. I'm going to close my part, start a new one, just so that we can see another round, basically, a part. It's just a line, right? So on a convenient plane, on that vertical plane, I will sketch a line 10 inches long. Let's make this in 10 inches. Okay. And exit. Apply material on it, made out of steel. And because the cross section is square, is non-circular, I need an orientation point. So what I'm going to do is I'm going to create a point here. Okay. And the point I'm going to create, let me see, where are we here? Okay. So the point I'm going to create it to be, just so that you can see it better. Let me do the following, cancel. I'm going to make this thing, make sure that it is actually on the XY plane, just to make it easier for me. This, control that, and I'm going to make it coincident, because then I know what the coordinate of the point I want to be. Definitely it has a Z of 0, okay, right there. And then I create a point with a coordinate, not on a curve, with a coordinate. This point cannot be on the curve. You already know that. That's the orientation point. Z is 0, but X and Y, it really doesn't matter. I'll make it X. X0 is fine, but Y of it, I will make, I don't know, 2. Okay, there we are. Oh, sorry. What I wanted, I cannot have a Y of 2 because it's going to be on the curve. So I'm going to make this thing 0, and I'm going to make it X of 2 or 3. I'll make it 2, fine. There, so there's a point there. That orientation point cannot be on this curve or on the continuation. That's something we already discussed in the lab on Friday, or in the class on Friday, on Thursday. Now, we're pretty much done here. Did I apply material? Yes, now I have to join it. Don't forget to join. The joining must be done There is no ifs and buts. It must be done either in wireframe and surface design or the big cousin of it, generative shape design. But anyway, it's right there. This is wireframe and surface design. For the purpose of our course, it's all you need to know. So that thing is joined. Very good. There is a joint. Let me save this thing. File, save management, save as. Let me go one level up, a new folder, and I'll call it frequency beam. I think that's what I called it. Yeah, that's good. We say fine. All right. Now we're going to go to the analysis and simulation, generative structure analysis. Here is the beam measure right there. Oh, we're not doing static analysis. We're doing a frequency analysis, right? Don't use static, use frequency. Now, in the event, just in the event that you didn't pay attention to this thing that says static, you realize that I don't need this. So what I'm going to do, look, here, right click, delete, and then you can go insert frequency. Sorry. Let me see for a second. Insert. Okay, there. Oh, yes. I deleted it, right? I deleted it. Let me go ahead and mesh it first. I thought that you can do it, insert frequency here, but it looks like you may have to mesh it first and then do it. So we go beam on that. This is 10 inches long, so I use 10 elements. Let me see if I can do that now. Insert, yeah, right here. So unfortunately, if you deleted it, you can immediately put the insert frequency, but you have to mesh it and then say insert frequency right there. Now, it says, what kind of restraints? Do you want new one or do you want something that you already have? Well, I don't have anything. I just say new one because I don't have anything, and there it is. Look, if you didn't delete that, or if you inserted the proper thing, then you don't have to worry about this thing. But in the event that you deleted that inadvertently, you inserted a static case and you deleted it, that's fine. You can either close this analysis, go back and get back into it, or just what I showed you. Good, good. Now, we already have the mesh. If you want to see it, right-click mesh visualization, the usual stuff that you do for beams. You don't have to do that. This is just to show you that it's meshed with beam elements, linear beam elements, and deactivate that. Good. Now the cross-section. You click on the 1D property, you select this, and I don't want it to be cylindrical, I want it to be rectangular. Click on the range, 1 inch by 1 inch. Okay, and it won't let you close it until you select the orientation. Look, right now it's kind of tilted. You can see that. You can see that. I don't want it like that. Okay, I want select an orientation point, and this is the point. Watch what happens to that circle thingy. Oh, right there. It rotated, and I can close it. So that's what I want. Very good. Now, this point is not clamp, simply supported means it's essentially pin. You click on the user define, you select this endpoint, and you select three translations. This point is on a roller, so you click on this, and you say, okay, if it's on a roller, this point does not move in the x and z direction. It can move in the y. And if you're only interested in the x, y, z, y vibration, that's okay. But this essentially is a roller. You can refine this thing by fixing some of these rotations, but I'm not going to do that. Okay, so that's fine. All right. And let's save the analysis. File, save management, analysis, save as. In that folder, frequency beam. And then we're going to say solve or compute. Oops, something I forgot to do. and we have to find out what it is. Okay, notice that this is not going to run because it says CPU estimation not available. So there's something that I have forgotten. Yeah. Okay. So notice that what happens, this, because I did not fix any rotation, this thing can actually spin about the y-axis as a rigid body. So what I have to do is to take away that spinning motion. I'm going to go here to another user-defined restraint. That same point, I could have done it with the other one, but no rotation about the y-axis, about two-axis. This prevents the spinning motion uh, while spinning motion as a rigid body. Now I'm going to run. Still not, okay, still not running. So there must be another issue here. Oh, I think it did run actually. Yeah, there. Okay, it did run. All right, all right. Now, let's look at this thing in the XY plane, the front view. XY plane in the front view. There. This is the first mode. If you double click on it, notice that we get 885. Remember we got 861? Very good. Very good. Now these other ones, these come in pairs. Because if you look at this, it's the bending in the other plane. In a different plane, essentially. In a different plane. You can see that. And then there are other stuff. There's other stuff here. This one is axial, probably axial vibration like that. And then there's some that are out of plane, second mode, etc. But this is the key. You compare this with what we got with solid element, pretty much on the dot. Very few elements, 10 elements, 11 nodes, whereas in the other one we may have had 5,000 nodes or something like that. And the result didn't significantly change. Now, what did I mean when I say be careful about symmetry? Okay, so let me look at from the front. Now notice that if you had used symmetry here and done only half of it, then the second mode would actually be, or the second bending mode may be missed. So for example, which one is the second bending mode? Let's see now, not this one, not that one, there. If you use symmetry and you said that, I'm going to model only half of it, this mode will be ignored. So be careful to use symmetry in natural frequency calculation and in buckling that's going to come up next. Okay? Again, you can plot the displacement, total nonsense. Right there, you can see that. Nonsense, 46 inches. Obviously, in beams, you cannot plot the stresses anyway. And that kind of handles the second problem, okay, which is this. And now we're going to talk about buckling. Okay, the second problem that I want to do is the concept of buckling, a very simple problem. Now, buckling, Euler buckling is what you did in the last maybe 2 weeks of your stress analysis class. And it dealt with beams because these are pretty much the only things that we can analyze or the simplest thing that we can analyze, and there is any hope of doing it analytically. But buckling occurs in three-dimensional geometries, and as you can see here, the fuselage of that aircraft has buckled. It doesn't mean it's going to fall off the sky. It's just that, hopefully that buckling does not cause a permanent yield, permanent deformation, and when the plane lands that or changes the condition of the flight, that buckling will not be dangerous. Okay, good. So for the let me quickly review what you did in the stress analysis class for Euler buckling. If you take a beam and depending on the end conditions and you apply a compressive load to it, it compresses, and suddenly it may snap or buckles. Okay, and these are dangerous things. In fact, the formulas that you're presented with analytical formulas are okay for start design, but you've got to be very careful because they make certain assumptions such as perfect, for example, manufacturing, no flaws, load being perfectly on the axis of the beam, etc. So actually structure buckle before this predicted load by, for example, Euler formula. And that's why they're called non-conservative. That means be careful, dangerous if you're not paying attention to some real situation that arise. Now, depending on the end conditions, the value of K varies. For example, if it's a simply supported pin at the two end, the value of K is 1, etc. And these are things that we did. Okay. So the problem that we want to solve is not quite this, but it is actually, uh, let me go ahead and show you what it is. It's this frame structure. It's this frame structure that we are applying a compressive load as shown. Let me go to the next slide. We're going to come back again to this. We're going to compress it like that. And when you think about this configuration, and if you're only interested in the buckling, symmetric buckling in the plane, you can see that essentially we have a cantilever, we have a beam here, pin, and it buckles. So it looks like it fits this description. So we are lucky that even this complicated problem, we can ask the Euler formula to come to our help, because this configuration, just look at this, for example, just look at this configuration. This configuration is exactly that configuration. But the load, you have to be careful. The load that make this thing buckle is P smaller than this P, using P times cosine of 45 degrees, which is P over root 2. Okay? So I can use this formula where K is equal to 1, where K is equal to 1. It's done here. But the value that I get is not going to be this P, it's going to be P over root 2. So there we are. And therefore, in this rather complicated problem, we know what the buckling load is. Now, because we are interested only in that mode of buckling and nothing else, then it is possible to pretend that this is on a roller, this is on a roller, because look at the drawing, the way it snapped or it buckled. It looks like this is on a roller and that's on a roller. I'm going to solve the critical buckling load according to Euler's formula is 29,000. The dimensions of the geometry are given, must be somewhere. Oh, yeah, the dimensions are here. So this length, 20 by 20, 20 by 20, that's what this L is, L, 20 by 20. And cross section is 1 by 1, so that's why we have R equal to 1 over 12. And it's made out of aluminum, right there, aluminum. Very good. First, I'm going to solve this thing with solid elements, and then we come and do it with beam elements. So let's go here. I don't need this. I don't need that. We start with the part file. All right. Immediately save it. File, save management, save as, one level up, new folder. We call this thing buckle solid. Buckle solid elements. That's what I mean. Because we're making it as a solid part, let me switch to part design. All right. And we select that sketch and draw that shape that you see. The shape that you see is essentially this. So this height is 20, and then this is 1 inch, okay? No, we're not using any symmetry at all, okay? except for that, the fact that I'm taking one quarter. Yes, of course, that is symmetry, I understand. But the depth-wise, I'm not using any symmetry at this point. So let's go, let me go ahead and do that. Okay, we already mentioned this. So this length is going to be 10. What is that, 10? Okay, very good. And this length is going to be 10. Okay. And this is going to be 1. And yeah, this is also going to be 1. I think that's what you've got, isn't it? 10. Yeah. All right. Let me see now. Is that the 1? I'm not sure whether this is a 1 or not. It looks like it's a little bit bigger than 1. Yeah, no, that's okay. Exit. Exit. And because I'm not using any symmetry along I'm not cutting it with the YZ plane for now. We're going to come back and repeat it later. I'm going to pad it by 1/2 inch in each direction. Mirror extend, 0.5 in each direction. 0.5. Okay, very good. That's what we got. This is made out of aluminum, so let's go apply material to it. Aluminum on this part. We say okay. We save it. Oops. Yeah, we save it. And later on, I'm going to come back and realize that, oh, wait a minute, there's a plane of symmetry YZ here. Can I cut it with it? And I will do it and show you what the issue, what happens. All right, good. So now we're going to go to analysis and simulation, generative structure analysis. We are doing okay. When you do buckling, first you have to do the static analysis. There is no ifs and buts. You have to do a static analysis first. Okay? Once you do the static analysis, then you can insert a buckling case. Now, one thing I forgot to do is that because of what I've taught you about about access system, corner system, uh, because I want to review that, although a problem can be done without using that concept, as I will be doing it when we discuss the beam model of this, but on purpose, I would like to create a coordinate system. I would like the coordinate system, which is like that. So, for example, axis 1 going like this, axis 2 going perpendicular to it. This is not necessary, but we might as well use the stuff that we have learned. Now, how do we create coordinate systems? We cannot do it in the analysis. You have to go back to the part, and remember, part, I can expand this thing, double click on it. Okay. All right, very good. And then there is axis system here. You can see that right there. See this axis system? It says, where do you want the origin to be? I want the origin to be at this location, but I don't want it like that. I want it to be rotated by 50 degrees, right? So what you can do is you can select this, put the cursor here, right there, right there. You see that? Right click, and you say rotation, and you say 45 degrees. About the x-axis, 45 degrees. Very good. So the load that I'm going to apply later is going to be in the z direction of this axis system. Why did I do it like that? Because I want you to know the stuff that I've taught you. One day it becomes handy. All right, good. So let's go back to the analysis. All right. Good. Now we're going to do a surface slider here, surface slider at the bottom. This is on a roller. So is this. You can put it all at the same time or separately. All right. Very good. And then I apply 1 pound load in the Z direction. You see this? P in a 45-degree direction, I'm set P equal to 1. Buckling means you tell me what P is. But buckling requires first doing a static analysis, so you have to solve this problem with a dummy load put in there. Then I make it 1 because it's easier. Here's a force. See that? Distributed force on that edge, but not the global coordinate system on the user coordinate system, this coordinate system, in the direction Z, minus 1. There. So this is in the user coordinate system, axis system 1, minus 1 pound, dummy pound. Okay. First of all, you have to do a static analysis. I'm going to run this thing. Right now, we haven't done any buckling or anything about buckling. This is just static analysis. You can see that. What is this? This is all static analysis right here. You see this? Right there. Static. Now, when I run this thing, it's going to bomb out. And hopefully you can see why, but let's do it and find out that it's bomb out and then try to use our imagination and what you have learned in the past 2 weeks, maybe to figure out what's going on. Okay. The reason, if you don't know the reason, maybe Katia will tell you. Click on this deformation, you can see what happened. Because this whole thing is free to move as a rigid body along the direction X. You say, okay, no problem. Deactivate this plot. Let's prevent that rigid body motion. Deactivate, and we go and say user define at a single point, and it doesn't matter what point. You can select this point, you can select that point. That doesn't matter. It doesn't matter. Okay, you can select this point. Okay, let's do that in the direction X, direction 1, not the global. Well, actually, in this particular problem, it doesn't matter whether you use global or axis system 1. It makes no difference because axis system 1 has the X aligned with that. So I'll just leave it like this. I'll just leave it like that. This will prevent rigid body motion. Okay, let's run it. This time, it will not give you any error messages. It will run. And in the event that you want to see the deformation, the problem is no problem, but reset your scale. Well, actually plot it, but reset your scale to default. There, nothing magic happens. I mean, if you apply 1 pound there, it just makes the whole thing shrink. This is not a buckling. This is just a requirement to do a static analysis with a dummy load. I use a dummy load of 1. You say, fine, no problem. Good. Deactivate. Now we're going to go and say insert buckling case. And as soon as you said that, it says, where is your static case? Did you do it? The answer is, yes, I did. And it's right here. And then I say, okay. And just run it. As simple as that. And let's see what will happen. Finished. Let's look at the deformation. For example, here, right click, not this one. You're in buckling case. Do the deformation. Okay. But this guy, let me hide that fellow for you. Deactivate that one. There we are. So double click on this. Sorry, plot the deformation right there. See that? I deactivated this because I want to see that guy. I don't want to see that guy. And I plotted deformation. And there we are. Double click. There is 10 buckling load that is created. And the first one is 26,000 pounds. 26,000 factor of, see, buckling factor 26,000. What that means is that take your dummy load of 1 pound and multiply it by 26,000. 516, and that is going to be your buckling load. 26,516 is buckling load. And what does that mean? do not use 26,516 because that causes buckling, first buckling. Now, what are these other things? These other things, actually, this is bad, bad, bad. Because what color mode is this? Turn it around. This is out of plane. That is not what I want. So misleading. But this one is in play. This one is in play. This one is in the YZ plane, and that is what we are after. We are after buckling mode in the YZ plane. This one was misleading. This is out of plane. This is what you can use to compare it with 29,000. Right on the dot, pretty much, very close to it. Incidentally, and these other ones, the other buckling mode. Usually when it buckles the first time, throw away your part. It's probably no good. Okay, it's the first buckling mode that you're interested in. Now notice that there's a lower buckling mode. In other words, if you had this fellow and you apply 26,000 on it, it will buckle, but out of plane. Okay? Just hypothetically, there may be constraints that prevents that buckling, then that's going to be safe, but then it buckles at 29,000 in plane. All right? Now, a couple of things just to show you the effect of the type of element. Let's see what this thing was. This was parabolic. Let's do it with linear and run it again. See how much that 29,000 changes. No problem there. Excellent. So let's go here, activate that, and double click on it. 48,000. I bet the first one is out of plane. See that? This one is what you're. It went from 29,000, which is 30 predicting, to 46,000. So look, type of element. Problem cannot be element dependent. So either refine the mesh. Now let's go here and refine the mesh. Let me go here and make it, this is linear. Let me go ahead and use a smaller element size. So I'll make it point, the problem is that I have to go and do the analysis, static analysis also. Please keep that in mind that, well, let's try. Static analysis must be done probably by default. So I go point, I don't know, 0.2. Run it. Yeah, I'm sure it's going to do static, and then it's going to do the buckling. So it should be taken care of. If not, we're going to fix it. Good, good. Double click. There we are. Yes, you see that? So when you use a finer mesh, it goes to 32 linear. A finer mesh but linear is 32,000. Okay? It should be 29, right? Theory says 29. When we use parabolic, even with that coarse mesh, we got almost 29. Very good. Now, what I want to do, cancel that. I want to go and actually cut this thing into two pieces. In other words, let's go back to the analysis. And I'm going to use the split in order to take only half of that. Split what? Split it with this. It doesn't matter what side you pick. There we are. Doesn't matter. Just make sure that you put a surface slider here later on. So we go back to the analysis. Back to the analysis. Let's see what we've got here. First of all, we have several restraints. This last one is the one that I prevented rigid body motion. I don't need that anymore. I'm going to delete that. But I do need a slider surface over here. Now, what I'm going to do is I'm going to go back to static. So look, right click. Let me first of all let me show you. Right click, set, what is that? Set as current step. See that underlined? Underlined because I want to put my roller, third roller on this face. Did I put it there? Yeah, it's over there. You can see that. So this is not going to have a rigid body motion anymore. All right. And everything else is fine. The rigid body motion is taken away. So let's go ahead and run it. Fine. First is does the static, then it does the buckling. So let's see now. See this, hide and show. Activate default. Let me delete this. I don't need that. Activate this. There we are. But this is the static. Okay. This is the static case that I don't want to see. Let me deactivate that. Let me activate this. Okay, so it looks like buckling was not run. So let's go ahead and run it. So let me do the following. Right click, set as current. And now run it. Deactivate that. Activate this. You know what? Let me delete this. Let me delete that and do it again. There. So it looks like I have to delete this. Now, double click on this. And notice that it gives me this value. This value is almost half of 29,000. Now, let me cancel this because you might say, wait a minute, oh, I don't recognize that number. I say, fine, you don't recognize it? No problem. Let's go back. Let's go back and put the original size, 0.659, whatever it was. And it was parabolic, right? Run it again. Because you might say, I don't recognize that number. I believe it. I believe it. Let's run it. Go here, activate. Double click. You recognize 14,000. But this, why is it different from that? Why is it half of that? Because this is the buckling load for the side that we model. There is also the other side that we are not modeling. So this is half the buckling load. Multiply this thing by 2, you get that guy, 29,000. Okay. I did not have rigid body motion because I put a surface slider on it. Okay. And this, because of the way I did it, it will only give you buckling in that plane, in the YZ plane, not the other ones out of plane. Good. I want to quickly repeat this problem with beam elements. So I'm going to kill this job and kill that. We have time. We're going to do that. I did it in class. So we go here. Part. Okay. I'm not going to save this. I'm not proud of myself either. On that vertical plane, I will sketch a 20 by 10 by 10, right? I do symmetry. I do only 1/4 of that geometry. So it's going to go like that. And I do dimensions here. So this one is 10. What is that? 10. Okay, by 10. Excellent. Exit. And because the cross section is not circular, I'm going to create a point here off that. So let me make x of maybe x of 2. Notice that it is created. It's right there. You can see that. Apply material on it. Made out of, this was aluminum, right? What was it? Can't remember. Yeah, aluminum. That's the property for aluminum. Almost the property for aluminum. Very good. Let's join this thing, but joining cannot be done here. You have to go to wireframe and surface design. There's the join icon. You select that. pretty much. And now we're going to go to analysis and simulation, generative structural analysis. Okay. And we're going to do static analysis. There's no doubt about it. First, we have to do a static analysis, then buckling. So it's okay. We need a static analysis, whether you like it or not. And then we are going to mesh it. Because we join it, the whole thing is going to get meshed. Yeah, fine. And then cross-sectional properties, select this. It's rectangular, size 1 by 1. Okay, very good. And orientation point is right here. Okay, that good? Ooh, wait a minute. That one is fine, but this one is not, okay? So let me do the following. Let me cancel that. Let me move this orientation point up there. Let's see what happens. Let me move it over there. In that plane. So I'm going to move this thing to some location here. I'll keep this thing as 0. Where is that? 0. And I will use a y of, I don't know, maybe 3. So it's right there. Let's go try it now. Go back to the analysis here. And now we click on the I-beam. The support is right here. And rectangular 1 by 1. And for your orientation point, I select this. That's good. That's good. Okay. This is not a random process. I asked you to see me if you want to know what. If it's circled, there's no problem. Good. And now we're going to, because this is a static analysis. First, we have static analysis. We're gonna put this thing exactly like what we had before. This is on a roller. So let's see now. It cannot move in the direction. I'm going to prevent the motion out of plane. So that means no displacement in X. And it can move in the direction Y. It cannot move in the direction Z. Cannot go up and down. All right. And yeah. So that's good. That's good. Okay. This fellow cannot move in the direction X because it has to stay in plane and cannot move in the direction Y. That makes it a roller. All right. And I'm going to prevent rigid body motion here. So one point, for example, this point, just not move in the direction X. All right. Okay. And we're going to put a dummy load of, now remember, in the solid one, I created this access system and I used it. I'm going to cheat this one. It's not cheating. It's just that, you know, the different ways of doing the problem. You click on that and you're going to say, okay, you know what? First of all, make sure that this is global. At that point, at that corner point, if this is bothering you, I'm going to hide it. Okay. At this corner point, I put 1 pound in the direction Y and 1 pound in the direction minus Z. So let's check it out. There, you see this? So this is going to be my dummy static force. Okay, so let's go ahead and run it, assuming that we haven't forgotten anything. Okay, this obviously we have to fix something. There's some probably rotations that we have to fix. Let's check it out. Yeah. Okay, so this thing, uh, yeah, because if you go here, notice that this thing does not rotate about the axis that's coming towards you. This beam cannot rotate about the axis that's coming towards you. So let's go ahead and fix this. So these are strains that I put in there. That thing does not rotate about the direction X. Okay. And this fellow also does not rotate about direction X. Let's run it now. All right, good, good. So let's look at the deformation. Reset the scale first. Reset the scale. This is a static analysis we're doing, okay? And it just compresses. You can see that. It just compressed, right? Just like before. It just compressed. Good. Now we're going to insert the buckling load. So insert buckling case. Static analysis we had to do, and we did it. It's right there. And then run it. And lo and behold, it should come out to be factor of 29,000. So you know what? Because we ran it again, we have to do the deformation one more time. Let me deactivate this fellow because this is for a static case. And click on that and double click on it. Better give you 29,000. It gives you close to it, okay? Now, obviously, this is supposed to be 29,000. We can change things. Let me see if we forgot anything here. No, that's good. Yeah. I want to make sure that everything is okay. You see now the view from the front. I want to make sure that we haven't forgotten anything obvious. This is good. Oh, 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 oh. Multiply by root 2. Divided by root 2. Because the buckling load that you're going to get is going to be because you applied your loads horizontally and vertically. Okay. The actual buckling load is that 20,000. Where's that thing? Where's that number? It was 20,000. It should be divided by root 2. No, multiplied by root 2. 20,000 multiplied by root 2. I'm going to use my phone here. 20,000 multiplied by 1.4. Yeah, 1.2. Root 2 is 1.4, roughly. So calculator. Let me get my calculator. Let's do it here. Calculator. Calculator. Okay, so 20,000 was 20,000 something, 400 multiplied by root 2. 1.414. I better get 29,000. Pretty much close. Close. Excellent. So we have done the problem. And good luck.